for whatever you're updating or trying to block or trying to hack, etc. So this is what it is. Oh crap, it's not showing the whole screen here. There we go. This is what it is, and you press any keys between any letters and any numbers, and it just creates babble. But when you run into these blue areas, you have to hit a space. And when you hit the red area, you have to hit an enter. And, well, that's basically it. When you see tab, you have to hit tab. Space, enter, tab, enter, space, enter. And now, if you hit the wrong thing, it crosses it out, and you can backspace it. And if you do too many, you can't backspace it. You have to press Control Z, which is the universal undo button. And so it'll allow a strikeout. So you have 2 strikeouts. It'll allow that. I went too far. It won't allow all that. Now it goes through, gives me a chance to fix my mistakes, runs the program, and then does a bunch of fake crap to make it look like it's a computer. And when it gets to the end, it gives me the score. I got a D, and it derives these values from some stuff. But imagine you're on your ship and you get a warning, and it says, you know, systems being scanned. You have to run over to the computer, and you have to play this little mini game, and it's timed, so how much code you can actually successfully get down matters. But basically anything that involves like computer hacking or anything to do with the computer on the spaceship will be played through this mini game. Okay, the next thing I have to show is, well, nope, not this sorting rhythm, but although this is a cool little thing that shows you how a bubble sort works. There's different sorting methods. I'm not going to get into that because that is not why I came here. Right here. So what you're seeing is a context tree being formed. And hopefully it's big enough on your screen. I don't know how to resize that. And that might be a little bigger. So let this play out. Now, each one of these white nodes that you see is a summary of everything before them. And actually, I'm going to pause this. We're going to roll back to just 1. Okay? So I'll add 1. Now, when I add, now we already had 1. That's this gray one. And that is, let's say, a chapter to a story. Then it adds another chapter to a story. Now it has 2 chapters, and what's going to do is it's going to take the 2 chapters and condense them into a single chapter. That's this right here. Okay? And now it has 2 more chapters. It's going to take those 2 chapters and condense them into this right here. Now what's crucial about this, and what makes my neural network really good with this, is that each bin contains the same amount of text. So we're always compressing 2 to 1. We're always taking 2 Corvettes and jamming them into 1 Corvette. And each time we do that, we're actually not losing anything. And so I'll add another one. Now we have 3. Okay, so this one and this one, the first 2, get summarized into this one. This one and this one, the second 2, get summarized into this one. And now this one and this one get combined and summarized into this one. So by the time we reach this layer, we have a compression of X4. That means that all 4 of these chapters of the story are now compressed into this one singular chapter. And so as we add these, it mirrors on the other side. And when it reaches every binary hard point, oh, I can zoom in on this for you. So first 2 summarize here, second 2 summarize here, third 2 summarize here, fourth 2 summarized here, and then these 2 summarized get summarized into this summary, and these 2 summaries get summarized into this summary, and then these 2 summaries get summarized into the grand summary. And so we'll keep adding them, and actually I'll play this. And as we add more chapters, these trees actually act like binary groups, or what you would call pairwise groups. And what that means is after I get to many chapters, let's say like 1,000 chapters, I only have about 9 groups of summaries that I have to actually read to read the entire book, start to finish. I'll pause it right here. It's a good spot. So right now we have, I'm looking at how many. I can't see how many, but it looks like we have about 25 to maybe 50. Hang on, it's 10. Oh yeah, probably closer to 60. Okay, and so we only need the white boxes from each side. So if I count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 summaries to read only 10 chapters to read all 60 chapters. So that's a 6x compression. Now you get more compression the longer this goes. So as the AI keeps adding summaries at each and every iteration, and this tree keeps growing, the whole thing, because of its exponentialness, means that it can grow basically unbounded, and I can always have the proper context to send back into the LLM. I'll pause it right here because we're at about 120 chapters. And at 120 chapters, we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. At 120 chapters, we only have 11 chapters that's like a times 10. That's actually more than times 10 compression. So as this thing grows, your compression gets better. And actually, I have the compression rates over here. And you can see that this very last chunk, this giant chunk right here that I'll zoom in on, is all getting crammed into a single summary. And that chunk, percentage-wise, forgot how to get to it. It's in here somewhere. Percentage-wise, it's a lot. So like right here, we're going from 129,000 tokens down to 25,000 tokens. But as this keeps growing, it gets better and better. Now, this is the story moving forward. This is what the story looks like as it's moving forward. There's these things called creators. There's a story arc creator, and there's a story arc author. There's a story chapter creator and a story chapter author. There's a story act creator and a story act author. And then there's the actual story writer creator and the actual story writer author. That's 8 total LLMs. They're constantly reading each other's context data. But there's more LLMs. There's these beacon LLMs that sit way up, way in front. And they sit wherever you want to put them, or wherever the AI creators want to put them. And these are solid beacons in the story that they're events that you know are going to happen. You're sure that they're going to happen. You just don't know how or when they will happen. And so those beacons do this exact same thing that we're looking at right now, but it actually plays it in reverse. So it actually tells a story backwards from the beacon until it handshakes with this node. And then these trees then can override the backwards beacon, but use the backwards beacon context as it flows forward, meaning that the handshake is really effortless. And now for the powerhouse of what this means. Each one of these is stored forever, each one of these tiers. So this is the spine in the center, and the spine is the raw story. That's, if you read that, you read every word of the story. And no matter what row you go to, you'll be able to read the entire story. So on this next row, you'll be able to read the whole story, but you only have to do half the amount of reading. On the next row, you can read the entire story, but you only do half the amount of reading. Same thing, same thing, same thing. So by the time you reach this top row, you're only doing about, a half of 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 the amount of reading. And you can read that top row across the whole thing, but then you don't really get super great rich content. Hey, I'm doing a video, so I appreciate if you stay quiet. Thank you. And so, basically, I can, every time a chapter is generated, I can generate alongside of that in a whole nother tree. And if I zoom in here, you'll see that there's 3 trees that are stacked right over top of each other. And there can be like 6, 8, 10, 14 trees, 100 trees stacked on top of each other. And each one of them are in parallel, and they contain information about that chapter. So let's say this red layer actually contains the abstractions of all of the player's choices, and the purple layer contains the abstractions of all of the outcomes of the player's choices. Then I can have a tree that's for causal events. I can have trees that are tracking tension, trees that are tracking relief, and all these abstractions and trees have their own system, just like this, where it gets highly compressed, and that allows me to take all of this context from all the abstraction trees, and the story creator can see those, and that actually helps the story creator develop the story moving forward. So it's actually a lot more complicated than that. That's about all I can fit inside of this video, but it's basically a neural net for story generation. It's a high level neural net for story generation, which means it's slow, but the tokens, the single token count, which is each one of these squares, holds thousands of tokens within them. So it's kind of my own architecture on solving memory for LLMs, because LLMs can only work with what they can fit in their brain, and they can only fit in their brain what can fit inside their context window. And so if I tried, generating 7 Harry Potter books, at some point the AI will no longer be able to see what it has once read before, and then it creates a butterfly effect chaotic mess when it comes to long-term story generation. So this is a way that the AI can actually access its previous memories in a super compressed way. And also the AIs can do really cool things, like you can remove every other letter of a book. In the whole book, you could take every other letter and remove it, which effectively makes the book half its original size, and an AI can read it just perfectly. An AI won't even skip a beat. So there's special tricks of compression like that. But anyways, peace out.